Hi, this is Tim Pack coming to you today with part one of a four-part series where we're going to be looking at in situ chemical oxidation steps. We've broken the series into four discussion topics: selection and loading, delivery, distribution, contact and persistence, reaction and destruction. We want to talk about those in each section of this four-part series. First off, oxidant selection. Selection is a process where you're evaluating the multiple complex site-specific factors associated with a site. And we've broken those down into three general areas: technology, site, and administrative. From a technology point of view, you're looking at what is the oxidant you're selecting, what is its predictive effectiveness, loading requirements, equipment capabilities, safety handling and storage, and availability at a site. The site conditions have to do with the site geohydrology or hydrogeology, depending on your focus. The site conditions, requirements, contaminants present, concentrations, locations, etc. And administrative, the time and cost, the contracts and liabilities, regulatory acceptance, and stakeholder engagement. Each of these three can be very important and indeed controlling factors at a site depending upon the site conditions. Once you have an idea of the contaminants of concern, you can construct a remedial screening matrix where you can look at technologies and their applicability for that particular site. And here we've seen an example for the Terra Systems remedial screening for a petroleum-related site. BTEX, GRO, naphthalene, etc. A couple points we wanted to make here. This is an engineering estimate based upon known data. By engineering estimate, I mean there's no single right answer. For this particular problem, you could see green indicating highly treatable. You could address this site by ISCO means or aerobic bioremediation means. Again, two different ways of approaching the same site. Selection is really based upon personal desire, contractor acceptance, site conditions, etc. So this was just a screening matrix. It provides a starting point available to evaluate, in this case predominantly ISCO and bio options, but you can certainly expand it to look at other things. This does assume uniformity and accessibility and available and neglects competing reactions, so it's a simplification of the remedial process. But as stated, it gives you a starting point to evaluate different things. If we look at ISCO specifically, a reminder that from an ISCO point of view, there are three major demands associated for oxidant, they being the stoichiometric demand, or the demand posed by the contaminants. It's an engineering calculation, redox equations, balancing ISCO versus the contaminant, and it gives you the mass requirements for this demand. The second one, and the most important one in any ISCO site, is the soil matrix demand, or the demand of non-target oxidizable compounds, things such as reduced metals, sulfides, organic carbon, non-target analytes, and a variety of other things. As shown on the graph on the right, this demand can be the major factor in looking at an ISCO program at a site. And finally, depending upon the oxidant, an allowance for the natural decomposition of that oxidant. These summed up together give you the total oxidant demand, or the mass of oxidant wanted to apply for the site you're taking a look at. So if we know the mass of oxidant in pounds on a weight basis, and we know the area we're trying to treat, or the volume we're trying to treat, I should say more precisely, you can start to look at, for that target area, how does that oxidant dose translate into what can be applied at a site. So we've picked a site, 4,000 cubic feet, which is 20 feet by 20 feet by 10 feet, or a pretty small area of a saturated sand, and we've calculated for our site conditions we needed 4,500 pounds of sodium persulfate. In looking at sodium persulfate, first thing you do is assume an application concentration. Here we've assumed 15% by mass, which is a typical application, generally in the 5 to 20%. If you decrease the concentration you apply, you increase the volume. If you're assuming 15%, that translates into 3,310 gallons of injectate that you're going to place into the ground. You then compare that to the available pore volume at a site, and you come up with the pore volume of 0.37 times, or in other words, you're trying to inject 37% of the available water in that target area. That's the volume of displaced fluid. The more fluid you're adding, of course, the more material you're displacing, the more difficult it is to get that material into the ground. So for this example, you can take a look at applying different strategies going forward. You could apply a higher concentration, a lower concentration, more mass, less mass, decrease your safety factors to put less material on the ground, etc. And this becomes the engineering estimate for going forward for the site. Certainly, Terra Systems is available to assist in any way. We look forward to working with anybody helping out on persulfate projects for ISCO or bio projects, ZVI-based bios, etc. Happy to help. Please reach out to us. Here's some contact folks shown up here. Happy to assist on any way we can on your project sites, and thank you very much for listening.